Good afternoon. I'm C.TARANTINO, and today I'm going to present to you the study on a monumental building affected by an unusual structural instability. The subject of this study is the Cathedral of San Lorenzo, a Romanesque church founded in the 12th century. In 2018, the developing of parallel subvertical cracks along the central nave walls of the building was noticed, and the Superintendency for Archaeology, Arts and Landscape of Rome required a vulnerability study of the cathedral. The request was to identify the causes of the damage affecting the central nave walls and develop a reinforcement project based on the principle of the minimum intervention. So we started a study of the building, analyzing the crack pattern geometry, planning a non-destructing diagnostic investigations campaign, and we made an assumption, an hypothesis on the origin of the damage that we verify with a numerical analysis conducted with the finite element software Abacus. The Cathedral of San Lorenzo rises in Viterbo, about 100 kilometers far from Rome, in Lazio region in Italy. The city is known as the City of Popes, since it hosted the papal seat in the 13th century. The building lies on the highest hill of the city in the eastern part of its historical center. It overlooks the main square of San Lorenzo, and it is surrounded by other relevant monuments such as the Pope's Palace with its enchanting and famous loggia and the old medieval house of Valentino della Pagnotta. The building was founded in the 12th century on the remains of an ancient Roman temple, and the original nucleus in Romanesque style had a limited extension, while the current structure is the result of numerous transformations and extensions carried out over the centuries and consequent to the increasing importance of the site. As it happened to many of our religious buildings in Italy, during the 17th century a new Baroque skin was given to the interior of the church. The bombing of the World War II caused many damages, and important restoration interventions were carried out which cancelled the stratifications and brought the building back to its Romanesque form. The current layout of the building shows a typical basilica scheme with three aisles, a transept contained in the building width, and three ending apses. The three aisles develops for 11 spans, scanned by monolithic columns in paper and stone and marked by double ring-round arches. Over the arches sequences, two walls elevate themselves beyond the lateral aisle's roof, defining the central nave space. The masonry walls, with an average thickness of 80 centimeters, are made of square blocks in paper and stone and thin layers of mortar. The foundation structure instead are of the shallow typology, and the three aisles are covered by a timber roof. In 2018, some cracks started to appear along the central nave, and here you can see the damage state registered in 2019. As you can see, the damage occurs in the middle of the walls and specifically at the level of the arches that separate the naves. The cracks are in the proximity of the keystones, and they start from the introduce of the arches and rise up for a few meters, disappearing immediately before the windows. The damage rarely involves the fracture of the stones, and the path of the crack follows the arrangement of the mortar lines. Upon closer inspections, the edges of the cracks appear coplanar and aligned, and observing the trend of the cracks and their geometry, a horizontal displacement seems to occur between the two portions of the wall defined by each crack. This kind of displacement suggests the presence of a traction tension that develops in the plane of the wall and acts parallel to its longitudinal axis. The trend and the configuration of the cracks looks very similar to that associated to some well-known mechanisms reported by scientific literature and also met in professional experience. I'm talking about mechanisms of foundation settlements characterized by a horizontal component, as those activated by natural phenomena like solifluction, the stone weathering, and some others. In this image, you can see the extreme consequences reached in some relevant cases. In our case, the hypothesis of foundation settlement is incompatible with the extension of the damage. Indeed, it is limited to a confined area of the wall, and the cracks present constant amplitude. And moreover, it would be inconsistent with the geomorphology of the site and the characteristics of the soil analyzed by previous geognostic studies. So the hypothesis on the presence of tensile stresses induced by a thermal variations came by observing an existing correspondence between the variation in intensity of the damage and that of the thermal conditions of the walls. We noticed that the crack pattern showed asymmetry in its location, but was prominent in the south wall compared to the north wall. Furthermore, the damage concentrated in the border region between the two areas characterized by different thermal conditions. The upper skylight, heavily exposed to the solar radiation, and the portico below, protected by the roofs of the lateral naves. Based on this hypothesis, we planned a diagnostic campaign of non-destructive tests. Ultrasonic tests were performed to estimate elastic and mechanical characteristics of the masonry. As it is known from scientific literature, recurring values of ultrasonic pulse velocity, referred to masonry, range between 1000 meters per second in the case of the presence of voids or fractures, and 2000 meters per second in the case of well-constructed walls. And the average value of velocity measured on the two walls is 3100 meters per second. So this means we are in the presence of a good masonry, which behavior can be compared to a wall made of rigid blocks. Also, tensimetric tests were executed to assess the stress conditions in the walls. Each test has consisted in the measurement of stresses value in the horizontal direction in 2 points vertically aligned. The first at the arch introdos, the second close to the cornice. The two walls are characterized by different stress conditions, while in the north wall the horizontal compressive stresses values are constantly detected. On the south wall, the values of the compressive stresses are significantly low near the cornice and frequently vanish at the arches introdos. This result highlights that there are tensile stresses acting in the region between the arches and the cornice, where the thermal variation is greater. Also, temperature measurements were carried out to estimate the thermal gradient along the wall's height and between the external and the internal face. The measurements were taken on the south wall, which is the most exposed to solar radiation, in the month of August during the warmer hours. We detected a temperature variation of about 12 degrees between the internal and the external faces of the wall. So we investigated the behavior of the wall subjected to a thermal gradient through a numerical analysis. We performed a fully coupled temperature displacement linear analysis with the finite element abacus software. The numerical model includes a significant portion of the colonnade consisting of 3 columns supported below and above by masonry bases, 2 arches, and a part of the masonry wall above the arches. It is based on the real geometric dimensions of the structural elements as well as on their constituent materials, represented by piperino of Viterbo stones for columns, walls, and arches. The mechanical characteristics of the materials are derived from the Italian legislation and summarized in the table that you can see here. All parts of the finite element model are modeled with brick elements. Masonry arches are modeled as single ashlars, while masonry and wall columns and bases are considered unique finite elements. As for the constraints, the columns are connected above and below the wall bases by a tie rod contact. The arches are connected to the walls by a surface-to-surface contact, and the same constraint is used between the ashlars. The structure is fixed to the ground by means of fixed supports, and also the 2 terminal parts of the colonnade are kept in full to simulate the continuity of the colonnade. The action deriving from unmodeled elements, such as the upper masonry wall and the above roof, are represented by a distributed load applied at the top of the masonry wall above the arches. A further boundary condition considered is that of the temperature of the external and the internal faces of the wall. The temperature values on these faces, that is 38 degrees on the external facade and 27 degrees on the internal one, refer to the experimental data recorded. And we also considered a thermal flow of 10 degrees from the bottom to the top to simulate the different condition between the part of the wall directly irradiated from the one below. The numerical analysis has been developed in two steps. The first step concerns a static general analysis. The second step deals with a fully coupled temperature displacement linear analysis. This type of analysis has been chosen because stress analysis is dependent on the temperature distribution in the structure, and the temperature allocation depends on the stress solution. The figure showed the result of the numerical analysis with a focus on the stress distribution in the model part represented by arches and the upper wall only. The result related to the summer conditions shows that a concentration of tensile stress with a magnitude very close to the one attained under experimental way occurs in the central part of the arches and in the above wall. This means that the orange area observed in the figure represents a potential damage zone where a crack pattern could develop. Contrary, in winter condition, it is noted that as temperatures decreases, tensile stresses values increase in intensity, but the extension of the masonry zone subjected to tensile action is reduced. As a result, in the cold season, the cracks tend to diminish their size with respect to those developed in the summer period. Going to the conclusions, we performed a damage analysis of the Cathedral of San Lorenzo in Viterbo. The structure showed an unusual crack pattern concentrated along the nave walls, not referable to classical noted instabilities and mechanisms. The analysis of the crack's geometry and the correspondence between the damage intensity and the varying of the wall's thermal conditions brought to the hypothesis of tensile actions induced by thermal variations. So we planned a non-destructive tests campaign, and we did finite element analysis with the software Abacus to investigate the behavior of the wall under thermal variations conditions. The results of the analysis are in good agreement with the stress values measured in the experimental tests and the existent damage scenario. Now, further developments of the study will evaluate more in detail the possible relationship between the recent onset of lesions and the variation in the irradiation conditions of the wall, probably connected to the ongoing climate change. Thank you for your attention.